Hello, welcome everybody to the One World Machine Learning Seminar. Today we are very excited to have with us Fred. He's a fifth year PhD student at MIT in the Department of Mathematics. He's jointly advised by Ankur Moitra and Elkanan Moser. His research focuses on computational learning theory, applied probability, and related areas. He's done some super exciting work in the space of graphical models and has recently been looking at developing robust algorithms for classic learning settings. Today he's going to talk about some work in that direction. And this is going to be on learning half-spaces under Massart noise, which has been a classic problem in learning theory. So please put your questions in the chat, and I'll monitor the chat and interrupt Fred at the right times. And with that, with no further ado, let's have Fred present his talk.
Thanks, Survey, for the introduction. Right, as Survey said, this talk will mostly be about half spaces and other classification models. This particular talk is based on a joint work with Satan, Ankur, and Morris. Okay, so how is this talk going to be structured? Basically 3 parts. The first part, I'll mostly just talk about the background. What is the Massart noise model? What is the prior work that existed? The bulk of the talk, of course, will be about the results. And at the end, there's a short section on sort of some proof of concept experiments that we did and how there are some possible connections to fairness there. Okay. So like I said, let's start with learning half spaces. Of course, it's a classic problem in machine learning. And the thing about half spaces is there's actually a lot of different models for learning them. So what do I mean by this? Well, here's a really simple model, which has several different names. It's sometimes called a well-specified model or a realizable model, or it's a pack learning model. And when I say model, it's a model for how the data is generated. So how is the training data, for my half-space learning problem generated? Well, I sample X from some distribution P. So X is going to be some kind of vector in R to the n. And then I give you a label Y, which is a supervision, and it's just whether it's on one side of the half space or the other. And just for convenience, we'll encode that with a +1 or -1. So this SGN is just a sign of this quantity W star.x. And like I said, the training data you'll get is a bunch of independent samples from this model. So X's are from P and Y are just whether you're on one side of the half space or the other. Pictorially, it's going to look like this, right? So W star is there. You don't get to observe W star, but you get to observe these blue circles, which are the minus labeled points, and these red triangles, which are the +1 labeled points. And there's a variety of algorithms that work to learn this kind of half space. So exactly which algorithm you want to use could depend on exactly what assumptions you want to make. But in general, all you need to do is just get all these points and find a half space such that all of the blue circles are on one side and all the red triangles are on the other side, and that works. And it also can be done efficiently with like linear programming. And so that's maybe the simplest and most classical model of half space learning. Now, and you won't get back the W star, of course, it's not possible in general, but you'll get back something else, which is a very good predictor for a new point, whether it's on one side or the other side of W star. And so the sort of complaint with that model is, in real world classification problems, you often, you're training a half space, often the data is not linearly separable. So you cannot get all of the minus examples on one side and plus examples on the other. And so what people kind of suggested as a better model is a model with noise. And this is maybe the most canonical model with noise is called the random classification noise model. And it's exactly the same, except there's a final step in the generation process where instead of always giving you the correct plus or minus label, with some fixed probability eta, which is at most 1/2, I give you the opposite label. So if eta is 0, it's the same as the model before. If eta is equal to 1/2, I'm actually just giving you totally uninformative labels. So that's why we should assume eta is less than 1/2. And it's actually somewhat less easy to get an algorithm that learns in this setting. Like you can't just use perceptron or just use linear programming, but in the 90s, people did figure out how to learn half spaces in this model by basically coming up with the right variants of those algorithms. And just a picture, this is what it would look like if eta is like around a fifth. It's mostly circles on one side and mostly triangles on the other side. Okay, so that's nice. But perhaps this model is still a little bit too idealized. And why is that? Well, one reason is that in a lot of cases, your noise level will depend on your example X. So for example, if you're doing like a crowdsourcing thing, maybe there's some kind of rare X for which your labelers are not so familiar with them. So they tend to make mistakes on those X more often than for the common X. And that's just one example. I mean, another thing that can happen is that for difficult examples near the decision boundary, maybe you make more errors on those. So there's a variety of reasons why the noise level might not just be a constant. And that's probably the main criticism of the RCN model. And so on the other hand, well, so we can try to come up with the most realistic noise model. And in some sense, the most realistic, you could say, is the most general because it captures every situation. And that's exactly what the agnostic learning model is. So what's different here is I don't make any assumption about how y is generated from x. So for our purposes, it's just a black box. And now we should be a little more careful to define what it means to learn, because there isn't even a clear concept of a W star baked into the generative model. So the goal, to be more precise, is really to find a predictor which is as good as the best half space. And when we say as good, it's measured in 0-1 loss, which is just the proportion of the labels that you get correct. And so some notation I'll use in the remainder of the talk is opt will always be the best possible. I guess opt will be the best possible misclassification rate. So in the realizable case, opt would be 0. And as the noise level increases, opt increases. And our goal is to get, as a learner, is to try to find a classifier which does almost as well as opt. And so that's what the second inequality says. We'd like the 0-1 loss to be upper bounded by opt plus maybe a little epsilon. And so this model is nice because it doesn't make any assumption about how y is generated based on x. Unfortunately, it has sort of the opposite problem. So it's kind of too general. So there are examples which are maybe related to cryptography, where if you could do agnostic learning, you could say break a cryptographic system, and we don't think it's possible. And so under various assumptions, you can prove that agnostic learning is impossible. And for example, Daniele proved a very strong result saying even weak and improper learning is impossible in this model. And so this kind of leaves us with the following picture, where there are the simple and perhaps unrealistic models on the left-hand side. There's the totally general and actually two general models like agnostic learning on the right-hand side. And there's this computational hardness barrier. And yeah, the simple ones are on the left-hand side, so we can do it in polynomial time. And the hard ones are on the right-hand side, and we really can't do much in those models. And a lot of this talk is going to be about this other model called Massart learning. And as we're going to see, this is really quite on the boundary between the easy and the hard. So what is this model? So it's a lot like the random classification noise model, but it changes this one part, that's the noise level can now depend on the example. And so as you can see from this diagram, it's exactly the same diagram as for RCN, except instead of a fixed flip probability eta, there's a general flip probability eta of x. And this is allowed to be a totally arbitrary function, arbitrarily complicated, as long as it's upper bounded by the fixed constant eta. So and eta is still will be a number that's less than 1/2. And so, okay, what does this model mean? Maybe as a story, there are sort of two good ways to think about it. One, which is particularly useful, is to think about it actually as a kind of misspecified RCN. So it's like if the flip probability was always eta, but the adversary or nature, can choose, for some examples, to reduce the noise level. So basically, they can improve the signal to noise ratio by picking for some x, eta of x is actually less than the maximum noise level eta. And from that perspective, you would think that there would be algorithms, because it sounds like that's a friendly kind of change that should only be helpful. Then if you're maybe, I don't know, maybe more of a negative way to view it is that it's kind of like agnostic learning, actually. And so what does that mean? Well, it's essentially the same as saying, like, there's for 1 minus eta portion of the data, they're generated according to the true, clean, realizable model. And then for an eta fraction, we give it to the adversary, and they get to generate the label in an arbitrarily complex way. And so those two become, mathematically equivalent. But somehow in one, it looks like we should be able to do something. In the other, it actually sounds kind of like, oh, maybe this will be difficult, just like agnostic learning. And because there's maybe two different intuitions which conflict, it's actually been a long-standing open problem to understand what we can do in this model. And it seems that the first person who asked this question was Sloan. In the 80s, also, it's been posed multiple other times by others. Oh, one last historical note, why is it called the Massart noise model? Actually, there's a very nice paper by Massart, in which he studied just the statistical question is, if you picked like the best possible estimator and don't worry about the computation time, how does it behave? In this model, it actually has really, really good statistical properties. So that's what Massart studied, and that's how it got this name. But for the remainder of this talk, it's actually not super relevant because you can't, in general, you cannot compute basically the thing with the best 0-1 loss on the training data. Okay. And so that's those are all the models. Now, what's the prior work? Well, their main actually thrust of previous work has been learning when you make some assumption on the distribution of x. And in particular, two popular ones have been that x is uniform on the sphere, or it's Gaussian, which is kind of similar to uniform on the sphere, or from a log concave. And there are a lot of interesting works studying these special cases where x is drawn from some kind of nice distribution like this. But those are just special cases of the general learning problem where you really want to handle any distribution over x. And actually, there was not much progress on this problem until this nice recent work of Diakonikolas, Gouleakis, and Tzamos. And what they showed is that in this model with like a polynomial sample complexity and polynomial runtime, they can come up with a hypothesis which makes error rate eta plus epsilon. And the way to interpret this is where it's really helpful to think about it as a misspecified RCN model. So in RCN, eta is equal to opt by definition. So W star is wrong, like is correct 1 minus eta proportion of the time. So in particular, this algorithm in the RCN model does get the optimal error rate. However, in the general Massart setting, because for some examples, the noise level can be lower, in general, we just know that opt is at most eta. And so it's not the same as getting opt plus epsilon, which is the normal learning goal. But on the other hand, you don't do any worse than if it was RCN with the maximum noise at every point. And so that's what they showed. And this kind of left two clear open problems, which they state at the end of their paper. One is that their algorithm actually, even though the generative model is from a half space and there exists a very good half space to classify the data, their algorithm did not output at the end a half space as the hypothesis. So they really output some kind of decision tree. So that's like an improper learner. And one of the big questions was whether you can do it properly, or maybe it's not possible actually. So in polynomial time, can you find a half space which has the same guarantee of getting error rate eta plus epsilon? The second open problem was whether we could achieve, instead of error eta plus epsilon, achieve error opt plus epsilon, which is the more standard goal in learning. And so that would be really to learn a half space which is essentially as good as the best half space on this data. So that was the main prior work. And from now on, I'll be talking about our results, which in particular answer those two open problems. And the part I'm going to go into the most details on is this part about learning half spaces properly. And first of all, I should explain why it's sort of the natural approaches, or the most common approach, which is basically to come up with some kind of convex surrogate loss, actually does not work in this model. And this is important to contrast with the case of the RCN half space, because you would kind of think, oh, we know how to do RCN half spaces. Maybe the same algorithm for the random classification noise should actually just work for Massart. And so it's good to know that for the RCN half space, as long as you assume margin, which for simplicity throughout the talk, we're basically going to be in the margin setting. there actually is a fairly simple algorithm where you just minimize some loss averaged over the data. The loss looks basically like this. It may be surprising that the loss function looks like this. So it looks kind of like the hinge loss, but on the negative numbers, the hinge loss is 0, whereas this loss actually goes negative. But it's good to know is that it actually comes from basically some general theory called the matching loss theory. And so there actually is some systematic way you could figure out that this is the correct loss to use. So it's not just an ad hoc thing. And so actually, you just need to minimize that loss, just like for logistic regression, you minimize logistic loss. If you minimize that loss, essentially, you can solve the RCN half-space problem. And we would call that an M estimator in general. And you would wonder why not just do M estimation for the Massart half-space problem. Maybe you have to tweak the loss. It's not clear. And the important context is that it just can't work. So no matter what function L you pick here, it's just not going to work in the Massart half-space model. And essentially, the intuition is that the convex losses like this, they're pretty sensitive to what happens for points which are far from the decision boundary, so where w.x is large. And just playing with that and using the fact that you want to pick L convex so you can optimize it, you can just come up with a few examples, and no algorithm like this is going to work on all of those examples. And so that says that probably our #1 most popular technique for solving this kind of problem just isn't going to work. And then DGT, they gave an algorithm which doesn't give a half space. And so it wasn't entirely clear how can we then go back and try to get a half space. And the trick is to use one of our tools in the toolbox, which is really Minimax Optimization. And the way to start is to think about, if we forget about actually computational and statistical constraints, maybe what would we like to do? And it turns out this is some optimization problem that you would actually really like to solve. So what is this optimization? There's 2 players, a min and a max. The min is trying to pick the half space W, and the max player is actually trying to reweight the distribution of data. And so C of x is just an arbitrary function, which is non-negative, and maybe has some normalization, like the expectation of C of x is 1. And the max player in this idealized game is allowed to play any reweighting function C of x. And the really, really important thing here is that no matter what C of x you pick, like no matter how you reweight the distribution of x, the joint distribution of x and y with the reweighting on x is still going to be a Massart half-space model. So why is that? It's because the Massart assumption is only a statement about the conditional law of y given x. So if I reweight the distribution of x in any way, say by doing importance sampling, it does not change the fact that I'm in a Massart half-space model. And that's really the crucial reason why we're putting this reweighting in. We're trying to take advantage of this. Now here's L of x. It's the same L of x from before. It's this Lipschitz. It happens to be the same as the Lipschitz function, or it's a RCN matching loss. And it was also used in DGT 19 in some way. And the fact, which I won't entirely prove, but maybe by the end of the talk, or you'll kind of see, is that actually if we could solve this idealized game and solve it to the global optimality, so it gets the optimal strategy for the min player, we would actually solve the problem completely. So it turns out any W which achieves the minimum of this the value of this game actually achieves error opt for classifying. Okay, and the reason is basically, as the max player, you would just pick all the points. You'll just pick to support the distribution in all the examples where my W is bad. And then you could get, and if I don't play W star, the true half space, then if the max player picks the points where I do badly, then this loss is, this expectation of C of x times the Lipschitz loss is going to be a large positive number. So that's basically the intuition as to why, if we could solve this optimization problem, we would get a really, really good half space. Now, what's the problem? Okay, last thing I wanted to mention is there's sort of a related problem that DK, Diakonikolas, Tzamos, and Zarifis, for this kind of general family of problems, this min-max framework is pretty natural. So they actually use a similar idea in an independent work for just a different problem, which I won't get into, some setting where you have distributional assumptions on x. So the details beyond the fact that they use the min-max game are actually not so relevant. But yeah, this is a very natural way to try to solve this problem. Now, what's the problem with this? It's basically impossible to solve this. And actually, it's not just a computation issue. Like, obviously, it's very hard to come up with an algorithm that searches over all reweightings C of x. But somehow the even bigger problem is just not statistically possible to do this. And why? Is because you could pick C of x supported on one point. And if I draw samples from like a Gaussian or whatever, I'm never going to actually get a sample that lands on that point. So even if you had like an infinite amount of data, you still would not be able to estimate this expectation on the inside. And so this formulation actually doesn't seem that helpful. And what we're going to do is we're going to throw away actually the convexity of this problem. So we're going to restrict the max player a lot to only play C of x's of a very particular form. And that's going to make it possible to estimate the expectation and actually going to lead to an efficient algorithm. And it turns out that the restriction we want to pick, which is not obvious, is we want the max player to only be able to pick slabs along the min player's direction W. And so more precisely, the C of x, the reweighting function, should be the indicator of point x where W dot x is small. So you're near the decision boundary and where it's upper bounded by R, and R is an arbitrary parameter. So that gives you the following optimization problem. And okay, so this is clearly a more reasonable setup in that the max player strategy is easy to evaluate computationally. And it turns out this is actually all you need to do. So the theorem we prove is that if you think about this from the W player's perspective, the inner max, this is just some function of W. And so that's just some non-convex objective. What we do is just do gradient descent on this objective, and we prove that if you do this and run for a small number of steps, you actually do get an eta plus epsilon learner for a half space getting air eta plus epsilon for the Massart half space problem. So minor details, okay, we can't evaluate the expectation, but we just estimate it over data, and that will be fine because of concentration. And one minor other detail is, if you think about it, it's not actually good to let me play any R, because what if I play a really, really tiny R and there's no data points which land in that region? I can't evaluate the expectation. So in reality, R ranges over slabs which have like a non-negligible amount of mass, but that's the kind of technical details which, after this point, I'm not going to, emphasize.
Fred, I had a quick question.
Go ahead.
So here you use the conditional instead of like using the total expectation, right? Does that make a
Yeah,
difference?
it's not, you're right, it's not an important difference. Yeah. Cool, thanks for the question. Yeah, and the last thing is I'm going to explain the proof in the margin case. So I'll explain what margin is formally in the next slide. But a similar idea does work in the case where you don't have margin. But it's a little bit simpler in the margin case. That's why I'll focus on that. And okay, so the mystery is why does setting up that optimization problem work? And in this part, the idea is definitely related to the idea in this previous paper by DGT. And what they did is they kind of figured out that something good happens if you use the leaky-Rayleigh loss in the Massart noise problem. And what they realized is if you just do M estimation with the leaky-Rayleigh loss, you don't get a good predictor W, because that would contradict the no-go theorem. But you get one that's actually good on some anti-slab, so the complement of a slab. So regions where the dot product of W and X is large. And that's good because if you can find some predictor which is good on a small set of your data, you can just fix your prediction on that set of the data. So this geometric region of points where W dot X is large, you fix your predicted labels to be signed W dot X. And then you just have a Massart learning problem to learn the complement of that region still. And so you can do some recursive thing and get a predictor which is good on the entire space. And that, that idea very clearly leads to an improper learning algorithm because you get some kind of lopsided decision tree. And so what's, if you want to view it this way, what's the insight is that actually, instead of looking at the anti-slab, we should try to look at the slab. And because the anti-slab is where W does well. So just from a gradient, gradient-based optimization perspective, we don't learn anything from the anti-slab. But on the slab, the complement of the anti-slab, we're not doing so well maybe. So there's a good chance that we could get some information there that's going to help us update W and get a better predictor. And so for describing the proof, let's just introduce some quick notation. So I just formally defined the Leaky-Rayleigh function. It's just a piecewise linear function with two different slopes on the negative and positive numbers. The Leaky-Rayleigh loss, L sub lambda, is going to denote the averaged loss over the data. And what does a margin mean? It just means there's no points too close to the decision boundary. So gamma is a parameter, and within a little strip of with gamma around the decision boundary, we don't allow for any points to be there. And so that assumption, like I said, is not essential, but we'll just have it, so it simplifies the proof. Okay, and so there are sort of two key lemmas to analyze the algorithm. So the first one, which is from this previous paper, is saying that the Leaky-Rayleigh loss for W star is quite good. And by quite good, essentially, the main thing you should know is that it's negative. So because the Leaky-Rayleigh loss, you saw that it has a part where it's negative, the loss can be negative, and this turns out to be important that W star gets a negative loss. And for technical reasons, we do need like an upper bound showing that not only is it negative, but like a quantitative upper bound. But the exact, I wrote it down in the slides, but the exact value is not super important. And this actually just more or less comes out by writing down the definition of everything and computing. So this is just one other way to write the definition of the Leaky-Rayleigh. Now what we do is we take the expectation over everything, and in our definition we had you evaluate the Leaky-Rayleigh at y times W star dot x. So this absolute value z just becomes this absolute value W star dot x. Then you have this indicator. You can take the expectation over y, and you get this probability that the sign is not equal to y minus lambda. So we just took the expectation, and this is what we get. Now, what's the key here to get that this is negative? Well, by the definition of the Massart noise model, the probability at any x point that the sign of W star dot x is not equal to y is upper bounded by eta. Lambda here is just a parameter which is slightly bigger than eta. So it's also upper bounded by lambda. And so this parenthesized term with the probability minus lambda, that's always negative. And so based on that, you see that the overall Leaky-Rayleigh loss is going to be negative. And if you use the margin assumption, you can get a quantitative upper bound. So that's the first lemma, that for W star, the Leaky-Rayleigh loss is negative. The second one, which is I guess the key new one, is to prove something about the Leaky-Rayleigh loss being positive. And this is where the slab shows up. And what we prove is that if you have any half space which is bad, so it has a big 0,1 loss bigger than lambda, then there is some slab along W where if you restrict to that slab, you get positive Leaky-Rayleigh loss. So this notation just denotes the Leaky-Rayleigh loss conditioned on restricting to this slab. And why is that going to be useful? Well, it's going to be super useful because this means if I have a bad predictor, then I can find a slab where my Leaky-Rayleigh loss is positive, and then I can use that to learn something about W star, because W star has a negative Leaky-Rayleigh loss. Okay, so how to prove this? Maybe like it's a proof by contradiction. Again, most of the trick is just to write things out, I think. So first, what's the definition? Okay, so we do a contradiction. So we assume for every slab, the Leaky-Rayleigh loss is negative. So I wrote out what that means. That's why we have 0 is on the left-hand side. Now, this is a trick that was used in the GGT paper and also maybe some other older papers where you just write, we don't like this absolute value of W dot x term because it doesn't look similar to the 0,1 loss. But what we can do is we can write, like we can use this identity that x is the integral of the indicator of y less than x dy. So write basically x is the integral of 1. And by plugging that in, we can use linearity of expectation and just rewrite this in a slightly nicer looking way where what I did is I just used that identity and this got rid of the absolute value. And what did it put in? It put in this integral. And because in the integral, there was this indicator y less than x, this became the indicator that s is less than W dot x. So I just plugged in that identity. Now, all we use about this integral is the fact that it is negative. And so that means that the integrand is negative somewhere. So you can write out what that means, then do a little rearranging, and you get something that has a very clear interpretation. So what we get is that for every width r, there's some smaller number s of r, so that if you look at the points where w dot x is between size s of r and r, then actually the predictor, the half space w, makes error at most lambda on that region, which is kind of like an annulus. So it's like a slab, but you took out the middle of it. And so that just came from the fact that this integral was negative. And if you think about that, if we have that for every r, then you can kind of imagine you start with a really big r, then you get a slightly smaller s of r, and you know that w dot x is that w is a good half space on that annulus. You remove that annulus, then you just apply this argument again, you'll get another annulus that the same half space is a good predictor on that other annulus. So you can do more or less induction to get down actually all the way and say prove that the half space w is a good predictor on the entire space. And that means that the error is at most lambda, which contradicts the assumption. So, or if you like, we prove is a contrapositive. So that's the proof of the key lemma. Okay, and from here we're pretty much set. So every step as the min player where I play a w and I suffer a positive loss. Sorry, I play a w and it doesn't have a good 0-1 error. Because of lemma 2, the one I just showed you, that means I'll pay a positive loss. And I know that w star would actually have experienced a negative loss. So overall, I'm going to experience a significant loss in the Lichirelu loss compared to w star. Okay, and why is that good? Well, the L of lambda is a convex function. And gradient descent has this great guarantee, which is that it's a low regret algorithm. So if I keep playing convex losses and I keep doing bad, the point I play is bad compared to the best fixed point, then gradient descent is actually going to learn a lot. And very quickly, it's going to find a point where I don't incur a lot of regret. So I'm eventually going to stop playing points which have positive loss if I update by gradient descent. And once I get negative loss, lemma 2 actually says, the contrapositive direction says I actually get good error eta plus epsilon. And so, yeah, that actually more or less completes the proof that you can do proper learning in this model and get error eta plus epsilon. So there's a cool application of this, which we'll call knowledge distillation, because it's essentially the same idea as knowledge distillation in the context of, say, neural nets. And this is actually sort of just a corollary of having a proper learner. And what it says is, suppose I give you access to a classifier H, which does say even better than eta. So maybe H gets error almost eta, or sorry, almost opt, or in between opt and eta. And I give you access to some samples from the Massart half-space model. I can actually convert from the classifier H to a proper half-space W, which is just as good as H, up to a small error term epsilon. And so how to interpret that? Well, we're going to see some examples of this, but basically, in the case where opt is less than eta, if we can come up with some other way to get a good classifier. So for example, I'll do a huge polynomial regression. This is a common trick in the literature that gets close to opt error, then that would be a really, really complicated hypothesis. But if we combine it with this theorem, we can then get a half space which has very good prediction accuracy and is as simple as possible. And we'll kind of think of H for the context of this is kind of like a teacher hypothesis, and W is a student hypothesis, and the student manages to learn from the teacher. Now, what's the trick? You can prove this theorem based on having a proper learner. It's not, I think, immediately clear, but the idea is very simple, it turns out. You just want to, how do we improve the student if it's not as good as the teacher? We just focus on the examples where the student disagrees with the teacher. And I claim that on this set where they disagree, the student must do worse than 50% on overall accuracy. So why is that? Because if you look at the set of points where the teacher and student agree, they have the same performance. So the difference in performance is entirely due to the examples where they disagree. And if the student got like a 51% accuracy on the set where they disagree, Well, the teacher is outputting the opposite. That means the teacher would have a 49% accuracy. So the teacher would actually be worse than the student. So on this disagreement set, the student has to be doing very badly. And once we know we have a set where the student is doing really badly, now we kind of know how to improve the student. So we use the same framework. And what we do is we just run the proper learner, but as the first step, we restrict to this disagreement set where the student disagrees with the teacher. Pictorially, there's some complex hypothesis and you have your simple hypothesis. And this set basically looks like S in the picture. Then once you restrict to that, you just run the proper learner step, like search for a slab and do a gradient step. And essentially the same kind of proof. Like because the student is just doing so badly on that set, essentially the same proof that I showed you is going to show you're going to make a lot of improvement. And within a small number of steps, you're going to get W to be as good as your original improper hypothesis, H. So a cute application. Suppose I want to learn half spaces, and now I am making a distributional assumption. So X is uniform over plus minus 1 to the n. Then in fact, even agnostically, you can get some results in this setting. You can learn to error op plus epsilon in time and choose a poly 1 over epsilon. But we only know how to do that improperly, and this is some huge polynomial regression. Now, suppose we're in the Massart setting. That's a special case of agnostic, so we can still apply that theorem. But now we can actually get to a proper learner, right? Because first we improperly learn, we get a really complicated hypothesis. Then we use the theorem I just showed you based off this minimax game. And at the end, we extract a simple hypothesis, which has error opt plus epsilon. So this is the best result. Well, first, proper learner beating error eta plus epsilon. And I guess the best result we know for learning Massart half spaces in this setting. And there's many other applications, as you can imagine, for with similar setups like this, where we first learn a good classifier using a complicated method, then extract a simple one. So the last thing I want to, or second to last thing, sorry, of the theoretical results. Okay, well, we said all this stuff about getting error eta plus epsilon and how if you have a teacher, you can do better. But maybe you don't actually need the teacher, or you can actually just come up with a better algorithm, get error opt plus epsilon. And it turns out that you can't. And the reason essentially has to do with a connection with some other classical work in learning theory on evolutionary learning. So I'm not going to give the full description of like what it means to learn a half space in an evolutionary way. But informally, the idea of the evolutionary model is you want to start with a half space W and then propose a set of new W, which are like the descendants of it, and do some kind of selection process, which hopefully results in a new W, which has the better 0-1 loss. That's kind of the idea. What's more useful for our purposes is to know it's equivalent to this thing called a correlational statistical query model. So this is a model where I do learning, but I restrict the ways that the learning algorithm can access the data. And so in the CSQ model, the only ways the algorithm can access the data is by making queries of the form, basically by getting estimates of expectation of f of x times y for an arbitrary bounded function f of x. And the idea is, if you actually have the data, you can just take the average over samples, and by concentration, that is a valid way to estimate this expectation. And so this is a way that we can consider a subclass of learning algorithms that only make a particular kind of query to the data. And it's non-trivial that this is equivalent to the evolutionary model, but it's a result of Feldman. And now the connection between this and Massart's really just has to do with this one equation. And what we do is we just, under the Massart setting, we consider a query of the form expectation f of x times y. And again, we do this trick where we take the expectation over y and we just evaluate that. And what you'll get is when you take the expectation over y, you get this thing on the right-hand side. So you have f of x that didn't change. Now, as the expectation of y given x is 1 minus 2 eta x times sine w star dot x. What does that mean? It's just another way to think of generating y is with probability 1 minus 2 eta x, I give you the true label sine w star dot x. With probability 2 eta of x, I flip a coin and tell you the output of the coin. So if you think about it that way, you get this formula. And if you think about this, it's actually the same as computing the same query under a slightly different distribution on x. So you can just think of this parenthesized term 1 minus 2 eta of x as a change of measure, which is saying, well, you made this query under the original distribution. I'm going to tell you the output under of the CSQ query under a slightly different distribution, but now there's no noise on y. And that's why we have the sign of w star.x in there. And OK, why is that useful? So actually, this would be a really good way to come up with an algorithm to get error 𝖮 plus epsilon. So that's actually somehow is the easiest way to think of it. So suppose there was a good algorithm for learning half spaces using only CSQ queries. Well, I can actually simulate noiseless CSQ queries in the Massart model by only making, whenever I make a CSQ query, I just get the result of the noiseless query on a slightly different distribution. So like if I had a general algorithm for learning half spaces that works in this very special CSQ model, you would basically just use the algorithm and it would be guaranteed to work for any Massart half space learning problem. So why doesn't that work? It's because we know there's actually no way to learn half spaces in CSQ. And once you realize this connection, you can, so that's a result of Feldman, and you can use the same instance from Feldman's proof to show that there's no algorithm which achieves error 𝖮 plus epsilon using poly 1 over epsilon queries. And this holds even when your x is drawn from a very nice distribution uniform on the hypercube. And this lower bound is for any SQ algorithm. Confusingly, SQ is, so the definition is very similar. You get to make queries of the form expectation f of xy. Now f can depend arbitrarily on x and y. It turns out that that's a much more powerful class. And actually, if you work through examples, like this captures all the proposed approaches to solving Massart half spaces, like all the things people did in the past with distribution dependent algorithms. All of these things that are based on, say, gradient descent on some loss, they can all be implemented with SQ queries. So as far as I know, pretty much every approach which has been proposed for this problem fits into the SQ framework. And what we see is that nothing that fits into the SQ framework is going to give you an 𝖮 plus epsilon learner. So it seems unlikely that there's any algorithm that gets error 𝖮 plus epsilon. When you understand the connection, you also see some connections between the Massart half space learning literature and the evolutionary algorithms literature, which I won't go into details on. And one last exciting thing is, the result I described is, it basically says you need like n to the log 1 over epsilon queries, which is tight in the particular setting we considered, which is conjunctions on the hypercube. You can ask if I allow for a much nastier distribution over x, does it get even worse? And there's this paper by Diakonikolas Kane, a follow-up work that shows that actually you get even a much stronger hardness result if you allow for really an arbitrary distribution on x. So that's what we know about lower bounds. One last thing I wanted to say from theory-wise, which I won't get into too much into the technical details, is you can think about actually models that go beyond this whole Massart half space thing. So another classification model we like a lot is the generalized linear model, where expectation of y given x is some nonlinearity applied to w star.x. So essentially, it captures half spaces by taking sigma to be a threshold function, but it's more general. And OK, we know how to learn normal generalized linear models. Now we can start to put in these Massart features where the adversary can improve the signal to noise ratio. So we'll call this a zero misspecified GLM if the adversary can move expectation y given x arbitrarily away from 0, so arbitrarily boosts the signal to noise ratio. That generalizes the Massart half space model. Now you can consider even harder models where its adversary can also move a little bit. They can actually decrease the signal to noise ratio, and we'll call it a zeta misspecified GLM. And what I wanted to say is, actually, in this setting, which generalizes the half space learning setting, we can still get algorithms that are robust to these kinds of adversaries. So more formally, you can get a hypothesis which has 0, 1 loss upper bounded by this thing on the right-hand side, where the first thing is the analog of eta. There was a generalization of eta for this setting. It's the error of the true half space under the clean model. There's a second term. I added this misspecification, so you kind of would expect to pay that in your error. Or you can think of the zeta equals 0 case, which is more like Massart. And there's epsilon, as always. So there's sort of a way to generalize all of this stuff to a seemingly much harder and maybe even more realistic setting, because now you can really model this thing where there's a lot of noise near the decision boundary. Yeah, and it's much better than if you were to just view the GLM as a Massart half space, because basically then you get 8 equals 1/2, and we don't have good guarantees for that setting, and it's not, well, because of the lower bound, not really possible in general. The one technicality is only when zeta is 0 is this proper. It just has to do with the whole minimax game. Really, that whole framework makes sense when zeta is 0 and doesn't make so much sense when zeta is bigger than 0. I'm not going to get into the details because of time. And also, what's the difficulty here? If you remember the DGT algorithm, it was kind of based on this idea: I'll find a slab where I get error eta plus epsilon. Now the concept of what is a good error to terminate is actually depends on the region. Because for like a logistic regression, for points that are far from the decision boundary, you actually need to get very high accuracy on that region to have an overall good classifier. And so this actually really complicates things, and it means it's not so easy to determine when to stop training your predictor on a region. It turns out, yeah, if you try to sort of naively consider, there's two cases. Either it's, I find a region that's much harder or much easier than the original region, or it's not much easier. You kind of can come up with some similar recursion that outputs the decision tree, but the recursion really blows up, so it doesn't actually work. And this part, no details, but there's a trick to get this to work where what you do is you forget about trying to learn a decision tree. You actually just try to learn a threshold circuit. At every step, you do a similar thing where you try to split the largest region and do some optimization of a leaky Rayleigh loss on this. But you throw in this other step that prevents everything from blowing up, where you merge similar regions. And somehow, if you combine those two, you can actually get an algorithm that works for this setting. So that's kind of high level, because this is, I think, the most technical part of the paper. But I think this is a very interesting setting. The generalized linear models with these adversaries, it captures a lot of the things about those models that we like. And it's one of the most general settings where we can do something. Finally, in the remaining small amount of time, I want to say a small bit about some sort of proof of concept experiments we did. Yeah, so okay, this part is not so surprising. If we already proved that, like, say, logistic regression, which is based off minimizing a convex loss, or minimizing the leaky Rayleigh loss, which basically works for random classification noise. We already proved that those can't work with Massart noise. And if you do experiments, you can confirm this. In our experiments, we also included, just for completeness, you can also try some kind of improper learner, like a random forest method. And it seems to actually do pretty well in practice in the instances we considered for Massart noise, but doesn't return a proper half space. So the first experiment was just, what happens with Massart noise? The green line is ours. Blue and purple are logistic regression and the algorithm that works for RCN half spaces. And as expected, our algorithm works much better. Yeah, in the right-hand side. In the left-hand side is RCN, and all the algorithms work basically the same. Now, the second thing I want to say is more of a proof of concept. Is we tried it on some semi-synthetic data with a real data set, which is the UCI adult data set. This is basically census data from 1994. It has some features. You probably may have experience with the census. Has some features about income level, ethnic background, languages, so on. And in this data set, what we set up as the classification goal is to predict whether your income is bigger than 50K or less than 50K per year. And here's the experiment we did, which is motivated by the fairness literature, is you fix a target group G. So for example, woman making over 50K a year. And then what you do is you actually add flip noise outside of the target group. Okay. And what we did is we did that experiment and see what happens to the accuracy inside of the target group. And the motivation here is, like, in the literature, you can kind of see that for this kind of problem, it's a sort of believed that the noise between different groups does indeed vary. And we want to see, like, if we inject even more noise, how does everything behave? And what you see is, yeah, that logistic regression really does not behave in a perhaps desirable way when you do this experiment. So here, the rows correspond to different target groups. And the blue line is logistic regression, and the green line is our algorithm. And what you see is that as you do this experiment where you inject more and more noise into the complement of the target group, all of the algorithms basically maintain the same overall accuracy. But in the target group, the logistic regression, basically its accuracy plummets. Whereas if you are to use the algorithm we propose in this paper, the algorithm for Massart noise, it actually, it maintains around the same accuracy level for even as you increase the noise rate to be quite high. So in this, if you're looking at least in this particular subgroup, I think what we're seeing is that this classifier output by this algorithm ends up to be better calibrated than logistic regression outputs. So, it's a purely experimental finding, but I think it's interesting, and maybe there could be some future work in this direction. Another thing you could try is like, maybe if you hide the demographic information, then you can fix this thing where logistic regression suddenly starts treating this group differently as the noise rate increases. But yeah, just if you do the experiment, you see that actually says logistic regression still has the same problem. Yeah, again, in these examples, the random forest does very similar to our algorithm, except that it outputs an improper classifier. Yeah, so those are some experiments. Well, first of all, showing that we can run our algorithm on the real data, but also suggesting that maybe there could be some interesting connections between this kind of, statistical learning theory with noise or robust statistics with some of the things that people are considering in the algorithmic fairness literature. And it would be really interesting to investigate this further.
Fred, I had a quick
Yeah,
question.
go ahead.
So in the previous plot, RCN
Yeah.
seems to be doing really well too.
This one?
Yeah.
Yeah, that's true. When you
Any reason for that?
hide the demographic information, for whatever reason, the RCN1 does get fixed and the logistic regression doesn't get fixed. I think it's just a coincidence. Like,
Okay.
there's no reason the RCN should work, but it does.
Yeah, it's surprising.
Yeah, it is surprising that it behaves so differently from the logistic regression.